Okay, so today we're gonna have some briefly introduction of what is the mechanical engineering design is. Basically, we have some courses related to the materials mechanics. Okay, so I think you guys already have took this course, as sophomore. Okay. Okay, so for this grading, we're gonna have this in-class assignment. So most of this assignment you have to take home, but you're gonna finish it in class. Okay, and we're gonna have two midterms and the one final project that is related to the final contest. Okay, we are gonna design a semiconductor robotic arm that can convey the silicon wafer, okay, from the starting point to the end point. And now it's a competition. So I'm going to announce this rule of the contest, okay, later of this course. Okay, and basically you have to bring your, any tape light, iPad, or anything. Okay, at least you can do your in-class assignment, and then you have to upload it, the PDF file to our education system. Okay, and delay upload is not permitted. Okay, it's not permitted. Okay, for this final contest, you guys have to arrange, you guys have to team up with 3 to 4, okay, in each team. Okay, and based on the final project that you designed by any CAD tool, AutoCAD, SolidWorks, anything. Okay, and based on that design, you have to manufacture your own robotic arm. Okay, so I'm gonna score. You're gonna get your score depending on the contest ranking. Okay. Okay, so I'm going to provide you some free 2D CAD tool like this LibreCAD or some AutoCAD for student edition. Okay. Okay, so let's start our course day. So as what I mentioned, this course is based on the materials mechanics. Okay, so that's retrospect some fundamental stress and strain from your mechanics course. Okay, so first is what is the axial loading? So let's have some definition of the axial loading. Okay, what's axial loading? Or say what's the loading, or what's the load applied to any component? How do you define whether this component will fail or not? What those parameters you have to know to analyze, a component is subjected to any forces, loading, or stress. Okay, so there are two examples here. So suppose we have this the beam with two boundary conditions, right? With two supports or two reactions. Okay, so for one component is subjected to 5 kilonewton, and for the other component is subjected to 1 kilonewton. And this component with 1 kilonewton is fail. However, the other one is still safe. Why? In these two conditions or the scenarios, what's the reasons that you could think of why this component just subject to 1 kilonewton, but it failed. But the other one with 5 kN is still safe. Why? Why? Okay, so let's look at this. kind of like look at this. So first, let's define what is stress is. I think it's quite easy, right? Stress definition as the force per unit area. And what is strain? The change of length per unit length. And engineering stress equals to the force or load divided by the original area, or we'll say the original cross section. Okay. And the true strength equals to the force or load divided by AI is the instantaneous cross-section area. Okay. And for the strength, for the engineering strength, equals to the change of the length, or say the delta L divided by the L naught, which is the original length, right? And the true strength equals to the integration of this elongation divided by the L, okay? Divided by L, okay? Okay, so I think you should be familiar with this conversion between the engineering strength and the true strength. Basically, what we can measure is the engineering strength. Okay, and then we can convert it to the true strength. Okay, convert it to the true strength. Okay. So you can imagine that for the true strength, because the cross section area is shrinking, right, during these tensile tests, right? And so the true stress will keep increasing, right? Will keep increasing. Okay. Therefore, the true stress is difficult to measure. And so we only measure the engineering stress for any engineering application, but not the true strengths. Okay, true stress and strain. Okay. Okay, so basically we can define the stress is the force divided by area, and the strain is the delta, the length change divided by the length, right? The length. Okay. So let's look at these three figures of this stress and strain curve, okay, from the tensile test. Okay, for example, for this, the first figure shows different polymers, like PMMA, ABS, or the HDPE. That's mean the high molecule polyethylene, right, and the low molecule weight of this polyethylene. Okay. So as we know, the slope from this stress and strain curve within the linear range, is the elastic modulus or Young's modulus, right? Therefore, we can say the elastic modulus can be regarded as its stiffness. Certainly can be regarded as its stiffness. So from this first figure, we can realize the PMMA has the highest Young's modulus, or has the highest elastic modulus, right? That's mean it has the highest stiffness, right? Compared to ABS or the HDPE or other polymers. Okay. For this second figure shows the difference between the true stress and strain and the engineering stress and strain curve. Okay. So what's the difference between this solid curve and this dot line curve? Okay. Within the linear range, basically, no matter it's engineering or true stress and strain, the slope is similar, is close to each other. Okay. However, as this the stress beyond, we say, the yielding point, beyond the yielding point. The differences between true and engineering stress and strain occur. Why? That's what I mentioned, because the cross-section area for the true conditions that the cross-section keeps shrinking, right, during the test. Okay. Therefore, they are the different curve. Okay. Okay. So the stress for the true stress and strain will keep increase. Okay. Till a fracture. Okay. So this curve can be converted from the engineering curve. Okay, from the engineering curve. Okay, so the third figure shows different type of materials under the tensile test. So, for example, suppose we have these materials A, materials B, and material C. So, can you tell what's the most possible materials for the curve A, and what is the most possible materials for the curve B, and so on for the curve C? So I will say for the curve A, the most possible materials is ceramics, right? Because it has the highest modulus. However, it fracture very quick. It fracture within a small strand, And for the materials B, I will say it might be a metal or some plastics, right? Maybe, I don't know. But from its curve, I think it could be some polymer, plastic, or metal. Okay. And this slope is much smaller than that of the curve A. Okay. And what is the most possible materials for the curve C? For this curve, the green one. Can you imagine if, oh wow, we can just give any materials that you can think of. It could be the elastomer, right? Like the rubber band. If you have watched the cartoon with One Piece, you must know the roof's scale is gum, right? Okay. Anyway. Okay. Oops, let's erase this first. Okay, therefore we can define the elastic modulus. Okay, we can define the elastic modulus. It's the slope of the stress and strain curve, right? Stress and strain curve equals to the sigma divided by the epsilon, the stress divided by the strain, right? And the stress equals to the force divided by area over the epsilon equals to the delta, the change of length divided by length, right? So we get as this components or any parts is subjected to the tensor, okay, whose elongation, or we say its displacement, equals to PL over AE. The E is mean the elastic modulus or Young's modulus. Okay. Okay, so that is from what we mentioned previously as for the actual load, right? Actual force, actual stress, and so on. So next we're gonna talk about the torsion. So what is torsion? Well, what's any circumstances that we have to take this torsion into account? circular shaft. Okay, circular shaft. So for torsion, we have to discuss the shearing stresses and strengths in the circular shaft, which is subjected to the torsion. And we're going to figure out what is the angle of twist and the polar second moment of area. And polar second moment of area. Okay, so for example, we have the shaft or the rod, solid rod. One end is totally fixed, right? One end is totally fixed. And we apply a torque. Okay, we just twist. Okay, we just twist a solid rod. Okay, and what's the shear stress distribution within its cross section? Okay, that's what we are gonna focus on, right? Okay, so when we apply a torque to a solid rod or a shaft, the shear stress distribution will be like this second plot. Okay, second plot. So the center of this shaft, whose shear stress with this torque equals to 0, and the maximum shear stress of this shaft with the torsion is the maximum. Okay, therefore the surface has the maximum shear stress. Okay, and at the center of the solid rod or the shaft, whose shear stress equals to 0. Okay, so it's a linear distribution from the center to the surface, from the center to the surface, from the center to the surface. Okay, so in this case, we can figure out what's the specific shear stress at a specific radius with this circular cross section, right? For example, we have this cross section like this. This is a cross section of the solid rod, right? And we're gonna figure out what's this small area, the A here. What's the stress applied to this small area? Right? Therefore, we can figure out, okay, so at specific radius, whose shear stress, right? And for the C is the radius of this shaft, right? So the maximum shear stress is located at the surface of this shaft. So there are two, in this case, this the triangle, right? Similar triangle. So we can use this similar triangle from your elementary, from the math, right? Okay, you already learned it from your elementary school, I think, or junior high, right? So we can just compare with these two triangle. So where is this? Right, you can compare with it. The tau that we are going to figure out, right, over the r, the distance from the center, and the tau max, the maximum shear stress over the radius of the shaft, right? So we can figure out this relation, right? This shear stress inside this the circular cross section equals to r divided by c times the maximum shear stress. Okay, therefore we say the shear stress at some specific location is a function of the radius, right? Right. Okay, and then if we just focus on the small area at the small area of the distance r from the center. Okay. So we say the shear stress equals to force divided by area. But the force here is the shear force V divided by the cross section. Right? Shear force V divided by the cross section A. And the force, the tiny, or we'll say the tiny force applied to the infinitesimal area is the F. That's the shear force. That's the shear force. Okay. Or we'll say the dF divided by dA in this case. Okay, therefore the force equals to tau, the shear stress times the area, cross-section area. And as what I mentioned, the small, very small force or the small shear force applied to this infinitesimal area equals to the shear stress times the infinitesimal area, right? Okay, so just make it quite clear. Okay, so this is what we got here. Okay, this is stress, the relation between the stress and the force. Okay, so what is the torque? Right, torque equals to force times, oh, should not be times, but is the cross. Okay, force cross the distance, right? Force cross distance. Okay. Okay, so in this case, okay, the F is the shear force cross the distance, or we say times. Why? Because the force right now is perpendicular to the distance r, right? Therefore, we can regard the cross as the time, right? You know what I'm saying? Okay. And then we can plot this dF, right? Tau times the A here, right? And we got this, right? We're going to take an integration for the whole area, right? Take an integration for this whole cross-section area, right? Okay, and then we can plug this tau right here, right, to here. And then we get this equation. Okay, and then we rearrange this equation. We get the tau max, the maximum shear stress divided by the C, the radius of this shaft, times the integration of the R squared dA. Right? Okay, so what we get. This is from the last slide, right? This term from the last slide equals to torque. And we just rearrange it. So the maximum shear stress equals to the torque, because we usually know what's the torque that we apply to a shaft, right? Times the radius, or radius of the shaft. You must know the radius of the shaft, right? Over this term, okay? Over this term. And therefore, we define this term as the polar-second moment of area, J. You can check the table or any handbooks or textbooks, okay? For different shape, what is polar-second moment of area is. So we get this final version of this for the shear, maximum shear equals to TC over J, over TC over J. Okay. Okay, so let's just review what's the the second polar moment of area. Okay, I think just take the review of it. Okay, if you're already familiar with it, just skip it. Okay, so we define the polar moment, second moment of inertia, right? This is our definition. Okay, so if we just focus on one tiny area of the shaft, of this cross section right here, okay, you can see this blue area, right? Okay, and we define the S equals to R d theta. Okay, d theta is right here, R d theta. Therefore, the arc, or we say the R, dr. Okay, the dr is right here, right? I'll just change the color. Okay, so the dr is right here, or say the S. Okay, right? So this equals to R times this. Oh, sorry, a little bit ugly. This theta. Okay, and the distance from here to the center equals to R plus dr. Okay, dr is this distance. So just select a small ring area. Okay, and then we cut this area. Just look at this small infinitesimal area right here. Right, what's the area of this? It's RDR, right? Or we say this S, the same thing. RDR, sorry, RD theta, sorry. Right? And this is DR. And we can regard it as the rectangular. Okay? We can regard it as the rectangular. That means the R d theta S as a straight line. That's a straight line. Therefore, the dA equals to R d theta dr, right? So I say this dA is the infinitesimal area. Therefore, we can regard this area as a rectangular. Okay. Okay, so let's go back to the this definition. Okay. So we have to take the integration of the whole cross-section area, right? So it's a double integration from 0 to R. Okay, 0 to R. And from 0 to 2 pi for a circle, right? For a circle is 2 pi for a circle. And R squared times the dA. dA is right here, right? Okay, so we just do some math. I'm gonna skip it so you can just check your textbook, okay? So just do some math work, okay? So we can finally we can figure out for the solid rod or shaft whose polar second moment of area is this pi over 32 times d of the power 4. Okay. So for the different cross-section shape, you can check the handbooks. Okay. Okay. Okay, the same thing there for the cylinder. If it's a tube, okay, if it is a tube, okay, so we can just modify the radius with the inner and the outer radius, right? Because we are not gonna integration from the center, but from the inner radius, Okay, so for this tube or cylinder, we get it the second polar moment of the area, right? For the cylinder. Okay. Okay, so what is twist angle? What is twist angle? So let's go back to the very beginning, that what we already know, the shaft is fixed at one end, it's totally fixed at one end, right? And we apply a torque, right? And the maximum shear is located at its surface, and the zero shear stress at the center. Okay. Okay. Okay, so when the torque applied to the solid rod, in this case, there are two angles. One is what we're going to figure out is the angle of twist, and the other one is the gamma. What is gamma is? We can regard it as the shear strength, a shear strength. So you can imagine that when we apply a torque, right, to a solid rod, suppose there's one point at the point P, let's say the point P, where you apply a torque, right, torque T, and this P will move to the second point, the other location, right? If we look at the side view of this solid rod, the P is going to move to the second point, the other point, or we say the point Q, right? The point Q. Point Q here. Okay, so from the side view, we're going to find the angle as called the gamma. Okay, so suppose at this without any torque applied, and we just look at the infinitesimal area here. Okay, here, right? Here, right? And then we apply a torque to the solid rod, right? So the point P will move to point P. Also, this area will move to the other area. Meanwhile, this area's shape is deformed. Okay, we'll deform it. Deform with the specific angle. And this angle that we call gamma. Okay, so we will deform from point P, right? Move to point Q, and the shape is changed with the angle gamma. Okay, it's gamma. And for the tensile test, or we say for the actual load, we define the stress equals to the modulus times the strength. However, for a torsion or for a twist, we define the shear stress equals to G times gamma. Okay, and gamma is the shear strength, the shear strength, and the G is the we'll say the rigidity, the shear rigidity. That's mean the ability to against the twist. Okay. Right. Therefore, the higher G value, that's mean this component, this solid rod materials has the high anti-twist property. Okay. Okay. And then we can define the gamma equals to the shear stress divided by G. Okay. Okay. So let's go back to look at the cross section. Okay. Okay. Previously, we just look at the side view, right? Now we just look at the cross section, the front view from this figure. Okay. So the S, that's the distance of the point P. The point moved from point P to point Q, right? The S. Okay, and this is R. So this distance is R times 5. Why? because this figure is quite the well, it's not the real case, right? For the real case, it's not possible to have this this huge deformation, right? It's a very small deformation for this portion. Okay. Okay, so therefore we can say the distance from P to Q is R times phi. Okay, equals to L times gamma. What's L? L is the length of the rod, right? L times gamma, right? This distance, this is the S, right? S and S, S and S, right? And then we just rearrange for this phi, the twist angle or angle of twist equals to L times gamma divided by R equals to L times tau over GR, and the phi, well, finally we got equals to T, the torque times the length of the rod over J, polynomial of inertia times polynomial of area, and the shear rigidity. Okay, and shear rigidity is similar to the E, Young's modulus, which is the materials property. Okay, which is materials property. Okay. Okay, so let's finish this example. Okay. Okay, so suppose we have this kind of this handlebar things like that, okay, and it's infinity rigid. That's a rigid body, and the materials for this handlebar is aluminum, whose the allowable stress is 10 kSi, and its shear rigidity is 3.9 times 10 to 6 psi. Okay, and if we apply the force, the point load at the point A, okay, and what is the required diameter of this rod? If we wanted the delta A is point A, right? So we apply a force, you're gonna have a displacement. Okay, this displacement has to be smaller than 1 inch. Okay, this is rigid. Okay, it's a rigid. It's a rigid, totally rigid. Okay, okay. So the torque, as we say, torque, you must know it, right? Equals to force times L, force times the length, right? The L is this distance, L, right? L. And the phi B, the angle phi B equals to TL over JG from the previous slide. We already know it, right? And this delta A, because it is rigid, so we can regard it as the infinitesimal displacement equal to L times the phi B equals L times the TL over JG, right? Because phi B equals to T over JG equals to L times the T equals to PL, right? Force times the length, force times distance. Okay, and it is a solid rod, right? So we know it's the polar moment of area. Okay, and this term represent the delta A, or we say the delta A is represented by this term, right? Okay, and we just rearrange this term. It has to smaller than delta A. Okay, and then we arrange this equation so that to figure out the diameter of the solid rod have to be greater than this term, right? Have to be greater than this term. And then we can plug in all those numbers, right? 100 pound, right? 100 pound, 12 inch, 12 inch. The length is 20 inch, 20 inch. Pi delta A that we define from in the very beginning is 1 inch, and times what? Polymorph area, right? Oh, sorry. Times the shear rigidity of aluminum, And then we get the diameter of this rod is, it has to be greater than 0.937 inch. Okay, so from this calculation. And then let's look at the shear stress. The shear stress equals to TC over J, right? Torque, that we already know it. The C is the half of the diameter, and the J, right, for the solid rod. For this turn, it has to be smaller than the allowable stress that this question tells you. Okay. Okay. And from this relation, finally, we get this diameter of this solid rod. Is, it has to be greater than 0.849. Okay, 0.849. Okay. So there are two diameter we're gonna select it. Okay, one is here, one is here. Right? So for this issue, we're gonna put the higher diameter for this solid rod. Okay, for the higher diameter of this solid rod. Okay, because the the allowable stress of the aluminum is 10 ksi, and when you apply the force P, the 100 pound here, will beyond this shear stress, beyond this allowable shear stress, 10 ksi. Therefore, we have to use the the larger diameter for this solid rod. Okay, for this solid rod. Okay, so today's course we're gonna stop here. Okay, and for the next course we're gonna start from the bending. Okay, from the bending. I think you should still already learn it from your mechanics, okay, materials course, right? Okay, so let's stop here.